Okay, the next thing we have to do is talk about specific heat capacity. And first we'll just talk about heat capacity. I hope you hear that there's a cat that wants to talk about heat capacity here as well. Um, Specific heat capacity. And you know heat capacity, it is the energy required to raise um, a unit of mass one degree. So this could be a pound mass. This could be a kilogram. A pound mass would be measuring at 1 degree Fahrenheit. A kilogram, a 1 degree Celsius. Okay, that's the heat capacity. And everything has a different heat capacity, and you're aware of this quite well. You're aware of this quite well. You are aware of this. It's late. I just gave an exam. Let's just think that you just made a pie. Kids and I are watching the Great British Baking Show. I think I mentioned this before, and they love it. They know more about baking and British terms than I've ever heard before. But let's just think that you're making this beautiful pie. Okay, and it's let's make it American here. So American is apple pie. Let's have a beautiful apple pie. Okay, and so you build this beautiful crust, your homemade crust, this pastry. It's beautiful. It's wonderful. And you go and you get some apples and you cut them and you slice them and you put some cinnamon and you put some sugar in them and you just make this wonderful filling to put in the pie. And then you just put wonderful, beautiful lattice work on top of this pie. Just a beautiful pie. And you stick it in the oven. Okay, and you bake it for, I don't know, 45 minutes. Does that sound good? 2 hours? I don't know how much longer you bake a pie because I eat the pie. But anyway, you bake the pie. And then you take the pie out of the oven. Okay, and you put the pie on and you cut it into 8 slices and you put it on the plate. Okay, and then it's just hot out of the oven. And so you wait until there's that perfect time where you can put your fork in it and put it in your mouth. And how do you do that? You blow on it. And you have some convection and some heat transfer heat's coming out of that pie. And then what happens is you think, this pie is beautiful. It's ready for me to eat. And so you put it on your tongue, and the crust is fine. The crust is good. It's warm, and you feel like this is going to be a great piece of pie. And then you get through that crust, and into your mouth is the molten lava, which is the inside of the pie, and you've burnt the inside of your mouth. You can't taste anything for weeks, and you just shout out after you somehow swallow what you have. You shout out as loud as you can, heat capacity, because that's just what happened. You took advantage of the heat capacity of the pie crust and of the gooey center of that. There was energy required to raise a unit of mass 1 degree. Well, the same thing is talked about the energy required to lower the temperature of something 1 degree. The heat capacity of the crust, it was much lower. It took a lot less energy to remove the heat from that crust so that you could actually taste it, touch it, and not be burnt. But that gooey center, it took much more removal of heat in order for that temperature to be dropped down. And so that same situation, we can have 2 different outcomes, and what ends up happening is you can't taste anything for 2 weeks. Okay, and so we take advantage of this all the time. Water is our perfect situation. Water has a very high heat capacity. Air has a very low heat capacity. Water is about 4 times the heat capacity of air. So when air, it takes a lot less energy to change its temperature 1 degree. But water, it takes a lot more energy to change its temperature 1 degree. And so that's why in the summertime, why your swimming pool, if it's 100 degrees outside, your swimming pool is still 75 degrees, because that energy is still more energy required to raise the temperature of that water. Conversely, when we're dealing with a power plant, we boil steam, we boil water, we take we take more energy out of that water as it lowers temperature, and that removal of that energy is what we use to run our turbines, run our generators, so that we take advantage of that high heat capacity. So it's a very valuable thing. Water is a very unique substance, and it affects our lives in many, many different ways, and that's one of the ways we can do that. Okay, so heat capacity. We call this heat capacity, we call this C sub P and C sub V, and where these are capitalized heat capacity. What we're primarily deal with is specific heat capacity, or as we call it, is specific heat often, and that's going to be equal to a lowercase c sub v and a lowercase c sub p, and probably I should, this is volume, so let me write it that way. Again, specific means we're dividing by mass, okay? And so what I like to think about is specific heat is going to be the heat transfer and the delta T that's required to make that heat transfer occur, okay? Now, what is C sub V and what is C sub P? This is going to be your quiz question for today, so pay attention to what I'm about ready to say here. C sub V is constant volume heat capacity. And C sub P is constant pressure heat capacity. And these are different things. These are different things. So think about it this way. I am going to get my piston cylinder here, my old friend, the piston cylinder, okay? And I am going to keep the volume of this constant, okay? And I'm going to want to raise, let's do here the air inside of this piston cylinder 1 degree. Okay, so I add heat to it. Okay, what happens when I keep the volume constant? When I keep that volume constant, heat's being added to it, pressure is going to increase in there. Pressure is going to increase in there, and we are going to just keep adding that heat until that temperature goes 1 degree. And so we'll find out how much heat needs to be added. Okay, now let's do the same experiment where we're now going to make this thing at constant pressure heat capacity. Constant volume, pressure changed. Constant pressure, volume is going to change. Okay, so here's where we start off here, and we'll say this is, I don't know, 5 bars, and we now want to raise the temperature of this air 1 degree. Well, as we're heating it up, the tendency of the air is to want to increase its pressure. But we don't want to increase the pressure, so we're going to release the pressure by changing our volume, and making it go up until finally what's going to happen is now we can say how the air inside of there raised 1 degree. Well, what happened in this case? We added energy, and in order to keep the pressure constant, we had to release a little bit to increase the volume. So the heat went in, and it not only tried to change the temperature of the air, but that energy also went into raising the piston. So with C sub P, you have to put in more energy to get the same outcome of 1 degree of change of temperature. So we know here C sub P is always larger than C sub V because of that volume change. Okay, this is a FE exam question all the time. Which one's bigger, C sub P or C sub V? C sub P is always bigger. It's always bigger. Okay. Now we defined C sub V as equal to the partial derivative of internal energy over the change in temperature when we keep volume constant. So this means at constant volume. And we define C sub P as the change in enthalpy over temperature, the delta H over delta T, F constant pressure here. And this is at constant pressure. Okay, that's the definition. Now remember, enthalpy is internal energy plus the pressure times the volume. So we have that pressure and volume thing happening here with C sub P. That makes some sense that this is how they're defined. And you don't really need to remember these things all the time. That this is something that you're going to need to have in the back pocket. But here's the one thing, and I will bring this up to you again as we go on, because we're going to see C sub P and C sub V in a lot of our equations. Just because they're defined as relating to enthalpy and defined as relating to internal energy does not mean that we always have to use them in that same way. Okay. Just because they're defined at constant volume and defined at constant pressure does not mean that we have to use them in a constant volume situation or a constant pressure situation. Okay, I'm going to say this one more time. Just because they're defined as a constant volume, under constant volume, does not mean we have to use it in a constant volume situation. And just because this C sub P is not defined as in a constant pressure situation, just because it was defined in a constant pressure situation does not mean we have to use it in a constant pressure situation. We could use it in all sorts of situations. Okay? Typically, we use it in situations where enthalpy is involved, and typically C sub V is involved with places that internal energy is involved. My analogy to this is duct tape. We have designed duct tape. We called it duct tape, but we don't look at that and say, this is duct tape. We have to use it in a duct. No, we use duct tape whenever we find something we want to tape together. Some people make clothes out of duct tape. We use it whenever it is applicable for us to use. Okay, we can't just say, no, it says the name is duct tape, we have to use it in a duct. Same thing happens here. C sub V, specific heat at constant volume, does not necessarily have to be used in a constant volume situation. C sub P, constant pressure, does not necessarily have to use it in a constant pressure situation. Do you notice how I've repeated this probably 3 times and you're tired of it? You probably fast forwarded through what I just said. It is a pivotally important thing that students mess up, and so I want to make sure that you have this under your belt so that you will not make those same mistakes. All right, C sub P and C sub V have units, and the units are going to be kilojoules per kilogram Kelvin, or they're going to be in BTUs per pound per degree Rankine. Okay, those are our units that we are going to be dealing with. Okay, now, the other thing I want to say to you is there's something called K. Now, this is different than the K that we talked about, that's thermal conductivity. This is just a regular K. I tried to draw the other K as a fancy cursive like looking K. This K is the specific heat ratio. Specific heat ratio. And so K is equal to C sub P all over C sub V. Okay, C sub P all over C sub V. So, C sub P is always in the numerator, C sub V is in the denominator. So tell me, is K always going to be greater than or less than 1? All right, is K going to be greater than or less than 1? The answer is it's going to be greater than 1 because C sub P is always bigger than C sub V, so it's greater than 1. All right, so this is how I remember. If I forget which one to put in the numerator, I always think of alphabetically. P comes before V, so I put the one higher in the alphabet, higher on the fraction. Okay. Let me just talk to you about this again. I said something about the C sub P of water, or H2O, is let's say at 300 Kelvin is equal to 4.179 kilojoules per kilogram Kelvin, and the C sub P of air at the same temperature at 300 Kelvin is or equals 1.005 kilojoules per kilogram Kelvin. Okay, now specific heat does change with temperature. As temperature changes, sometimes it takes more or less heat or more or less energy added to a substance for it to change the temperature. It's not a constant that says, well, when water's 500 Kelvin, it takes the same amount of energy to change it to a degree as it is when it's 200 Kelvin. That's not the case. It does, there is a change that we can see there. It goes up and down, and we'll look at our books and find out what those C sub P values are later on and be able to work on those. Okay. We can use C sub P and C sub V to help us find a lot of properties. We'll talk about that a little bit later. But the things you need to look up are, there will be tables A19 through A21 are going to be your tables. Let me see if Okay, I had to reboot my program here, but let me show you here what I want to say here. Properties of selected solids and liquids. Here's where you can find C sub P. Table A19, C sub P. Here's where it is, C sub P for all sorts of different solids. And notice they're looking these up at 300 Kelvin. Okay, and we look down here, building materials, insulating materials. The very bottom of this page is going to show you for liquids, and then it's going to show you for water at a lot of different temperatures. So notice how the specific heat changes. It goes from 4.2 to 4.17 to 4.18 to 4.19 to 4.22 to 4.256. So it does change as the temperature changes. It's all around the same value, but there's a slight change that happens inside of there. That is table A19. Table A20 is going to be ideal gas specific heats at some common gases. It's going to show you different temperatures. Here in the English tables, it's going to show it to you in Kelvin. C sub P, C sub V, and then it does the C sub P over C sub V and gives you the K value for that air. It gives this to you for 6 common gases that's provided down. Now, I want to show you something, because this table A20, the temperatures in Kelvin for this, let's go to our English table A20. Table A20. Look what happens. They reference this table, same gases, they reference it in degrees Fahrenheit. So please pay attention to this when you're doing it. I would highlight this and make sure that you don't make a mistake, because I all the time am looking at my temperatures in Rankine here, and because I'm used to do it in Kelvin, and I'm making a big mistake, and I'm off quite a bit by 460 degrees off of what I should be doing. So make sure that you know that that's there, and you don't make that mistake. The next thing to show you is the last table that deals with specific heat is table A21, and this shows you the variation of C sub P bar. So if we put this on a molar basis with temperature for selected ideal gases. So this is all sorts of other gases that maybe not be given in that table. Here's what we would do if we wanted to find out what the C sub P was, and it's an equation, alpha plus beta times temperature plus gamma times temperature squared plus delta times temperature cubed plus epsilon times temperature to the fourth. Here is what, if you were to use a computer program and you said, I want to let the computer calculate what the C sub P value would be, you would put in this table of data and you would have the computer be able to calculate the specific heat value using this type of equation. Here's the thing I'm going to tell you. We're not going to use this in this class. This is not something that we want you to use. We will use something down here in the footnotes of this table, but this table here is not something that you're going to see used in this class a lot. Okay? Or at all, actually. I think that ends our discussion about specific heat.